Welcome to Lecture 31B. Here basically we're going to apply the divergence and Stoke theorems, that is the 2D or 3D representation, under problematic conditions which I'll define shortly. So the material for this lecture comes from Reading Assignment 4, Section 4.7, and the objectives are to show how the divergence theorem, Stoke's theorem, and Green's theorems, which are essentially the 2D analogs of the divergence and Stoke theorem, can be used for irregular regions or when the field is undefined at one or more points in the region or on a closed surface or closed contour bounding a region. So the concepts and visualization skills we'll be dealing with here are introducing cuts to create regions which are enclosed and adding contours or surfaces that avoid points at which the field is undefined. As usual, the second slide is just a summary of the slides to follow, so I'll just move on to the next slide. Okay, so we're going to apply the divergence and Stoke theorem if a region is not simply connected or simply enclosed, or the regions contain problematic points. We'll get into what these things represent shortly, but I just put everything there in terms of very sort of short summary statements. Now, up to this point, when we applied the divergence theorem, Stoke's theorem, or Green's theorems, we basically made some assumptions regarding the nature of the fields and the surfaces or regions or contours that we're dealing with. And so I've just basically written down the various cases basically that we'd be interested in making sure are in fact valid. So first of all, the partial derivatives of the vector components are continuous within the domain for a divergence theorem and on the surface for Stoke theorem's problems. Surface, of course, doesn't have to be flat, it can be curved. The vector valued functions are continuous on the closed surface for the divergence theorem and on the closed contour for Stoke's theorem. And third, a closed contour must completely enclose an open surface for Stoke's theorem, and a closed surface must completely enclose a domain for the divergence theorem. Note that a domain in 3D is a volume and a domain in 2D is a planar area. So I just make this as a statement because I'm not going to repeat this. I just say either region or domain, and it's implied whether or not we're dealing with a 3D problem or a 2D problem. So the general question is as follows. Can we still use the divergence theorem, 3D, Green's flux theorem, 2D, Stoke's theorem, 3D, and Green's circulation theorem, 2D, if one or more of the conditions stated above are not valid? And the answer is yes, but we'll have to find ways of circumventing the problem so that the new problem basically is one in which all the conditions above are satisfied. So first of all, let's look at classification of contours and classifications of regions, starting with basically 2D and then moving to 3D problems. So for contours in 2D, we have basically terminology that's being used. And so we characterize contours as being simple versus not simple and closed versus not closed. And now if you take all possible combinations of these two, there are 4 in total. And so I've put a little table on the side here. Simple, not simple, simple, not simple, closed, closed, not closed, not closed. And then a simple diagram to illustrate these 4 conditions. So this would be considered a closed simple contour, and this is a problem that we've been using all along. So there are no problems with this one. Closed, not simple. All right, so this one is potentially problematic because you have a crossover point here. And so you have to sort of keep track of what's going on. There's a region here and it's a region here. So in principle, this is a problem that could be solved, but you've got to keep your eyes on this one. Not closed and simple, not closed, not simple. Clearly, we're not going to be able to use, for instance, Green's circulation theorem or flux theorem here because it's required to have a closed contour. But nevertheless, this is just showing you ways of characterizing contours. So again, I just mentioned that a curve which is simple does not have any crossover points. Notice there's a crossover point, so this is not a simple curve. And also closed curves enclose regions. So for instance, this encloses this planar region that you see here. All right, now let's classify regions. Okay, so There are basically two things that are used to characterize regions. One is whether or not the region is connected versus not connected, and is it simply connected versus not simply connected. Again, there are four possible scenarios, which I basically have outlined here in the table. So let's look at each one of these in turn. So for instance, this type of region would be considered connected and simply connected. And these are the regions that we've been looking at in problems so far. This would be considered not connected and simply connected. And so these are like two islands, but each region separated from each other could be treated quite nicely. Here, on the other hand, we have something which is connected, but not simply connected. And what does that mean? If you, for instance, take any contour within a region and you try and shrink it to zero, in other words, smaller and smaller, if this contour, when you keep shrinking, remains in the region, then there are no issues. But the moment that you find that you have to basically go outside of a region in order to shrink this contour to zero, then basically we have a not simply connected problem, and that is problematic in terms of applying either Green's flux theorem or Green's circulation theorem. So this is a real problem that needs to be solved. Here we have not connected and not simply connected. So here, for instance, this is the same as this one, and you have two different regions. So in principle, we could solve this type of problem, but the headache is to deal with this, and that's basically what we're going to be outlining. So in general, connected region just means no islands, and simply connected region implies every closed simple curve does not overlap, can be shrunken down to a single point without exiting a region, i.e. no holes. All right, so for instance, there's a hole. All right, so now let's look then at not simply connected 2D region, and we want to figure out how do we basically make this amenable to the use of Green's circulation theorem or Green's flux theorem. So this, as I said, is a connected but not simply connected 2D region. So what we've drawn here are contour 1 for the outside and contour 2 for the inside. These are just directions I've chosen to be both counterclockwise. So how are we going to basically create a contour that encloses the region shaded in gray? It's very simple. What you do is you introduce a cut. You cut this basically right down the middle here. And what you do is you have these two lines that you see here infinitely close to each other. They more or less overlap. But here we're just showing, for sake of argument, that they're very close to each other. So if you look at this now, this basically represents four different segments. When taken in total, enclose the region, which is the area shaded in gray. So we have, for instance, here C3, C1, C4, followed by C2. Now, since we chose C2 to be counterclockwise, minus C2 means clockwise. So this is clockwise. C4 and C3 are new, so we've just given them a specific direction. So this more or less solves the problem in terms of having a contour which encloses the region. And so now basically you want to figure out what does Green's circulation theorem and Green's flux theorem look like when we introduce this cut. So that means that a closed contour here will have four contributions as shown here. This is for Green's circulation theorem. So the contribution of C1, C4, minus C2, and C3. Again, minus C2 just means you're moving in a clockwise direction versus counterclockwise direction. All right, but if you look at these two, one going this way and one going this way, they're going in opposite directions, but each makes a contribution to the closed contour integral, which means this term and this term, when added together, right here, sorry, the term here, C4 and C3, when added together, this is opposite sign to this, so when summed, gives you zero contribution, and as a result, you end up with C1 minus C2. Now, you can also basically change this around. So for instance, minus C2 is clockwise. If you were to have made this counterclockwise, then you could do it, but that would introduce a minus sign here. So effectively, we can write it this way, or we can write it this way, but this depends on how we decide to label our contours. And if we do that, then it does enclose the region, and so the right-hand side basically of the circulation theorem does not change. It's only the left-hand side that changes. For the Green's flux theorem, it's identical. Instead of dealing with TDS, we're dealing with the normal, NDS. So effectively, you end up with a similar sort of relationship. So here we had C1 and a minus C2. We have a C1 and a minus C2 here. And this now is the flux, whereas here this was circulation. Again, A represents a gray, shaded gray planar area in the XY plane. All right, how do we address a problematic 2D region? So for instance, you might have 2 points here where the field doesn't exist, right? No limit. And so we cannot integrate over a region. And so the simplest thing to do is avoid it. So what we've done is put 2 closed contours, right? One closed contour here around this point and one around this point. So we've encircled it. But that's still not enough, because if we're going to apply the green circulation theorem, we need to basically have a closed contour that encircles the region. And so the simplest way to make that happen is to introduce a cut that goes right across. And so what you end up with is 2 separate regions or subregions. And each subregion, we can basically have a contour that encloses that subregion. So here's one subregion, this gray area, and here's the second subregion. And I basically distinguish this to be the bottom subregion and A, the top subregion, right? So the cut allows us to do it. And so if we're interested in the problem as a whole, we could apply either the green circulation theorem or Green's flux theorem for this one and this one, add the results together, and we would end up basically with a formulation of either of the Green's theorems, which now basically is valid because we have avoided the points in the region which were problematic. Note, this is similar to what you would have done in MAT290 for Cauchy's integral formula, where the poles are enclosed by contours to help you solve the integrals. So just make reference to this figure in the next couple of slides. You can flip back and forth if you want. There's not enough space, so I just didn't repeat the figures. All right, so let's take Green's circulation theorem and then Green's flux theorem. So applying Green's circulation theorem, we've got the top and the bottom. So you can see subscript A and subscript B. So this is the closed contour for the top sort of half circle, and this is the closed contour integration for the bottom half circle. So this is the left-hand side of Green's circulation theorem for both cases. All right, so now what we're going to do is we're going to take these 2 equations and add them. All right, plus. So we're going to add the green and the yellow equations together. All right, so what does that basically do? That basically means that on the left-hand side, when you add these together, basically you'll be going around the whole contour. And these basically now, when we add them, we have to make use of the fact that TS4A is in the opposite direction to TS4B. And TS5A is opposite to TS5B, and TS6A is opposite to TS6B. So when we add these 2 together, you're going to start getting cancellations of these pairs. So you're going to get a cancellation of a pair, and a pair. And so we're left with then basically only 3 terms left over. And so finally we end up with FC1 minus C2, because this is basically going in a clockwise direction. Alternative, you want it to be counterclockwise, then this becomes C2, but then we have to introduce a minus sign here, similarly here. And so you could also write it out in this fashion. All right, so this is perfectly okay now. And so this now would represent the region, right, over which we'd be integrating, excluding the area of the 2 problematic points. This, is, of course, would be the right-hand side. So this is more or less the formulation of Green's circulation theorem in the event that you had, in this case, 2 problematic points. Note, you can extend this to the 3D case by invoking Stoke's theorem. So instead of having a surface that's planar, there'd be a surface which is curved. But you could have problematic points lying on a curved surface, so more or less you'd be invoking the same sort of arguments and basically showing that Stoke's theorem can still be applied, even if there are problematic points on the surface. All right, Green's flux theorem is more or less exactly the same, except now the tangent vector ds gets replaced by the normal vector ds, and so I won't go through this in any great detail. Everything is more or less the same. You have to add them, right? And so in the end, you end up with something that looks very similar, except the ns is now instead of ts's. Note the direction of NS is to your right, pointing outwards when traversing a closed contour in a counterclockwise direction. This is a convention, and we're only talking about closed contours. So it has to be closed, otherwise this has no meaning. Secondly, we just already alluded to it, a closed contour integral taken in the clockwise direction, which I call minus c, that's why it's shown as minus c here, is equivalent to going counterclockwise, but then that introduces a minus sign here. So these expressions are equivalent to each other. All right, how do we extend the concept of connectedness simply connected in problematic regions to 3D, which means applying the divergence theorem and Stoke's theorem? So I've just repeated the figures here, and then I'm just going to sort of make a sort of an assertion that in 3D, we basically are just talking about the geometries being different, but the concepts being more or less the same. So a contour in 3D, that means a contour lies on a curved surface in 3D. So if we're going to invoke Stoke's theorem, then we're dealing with contours. A region in 3D. Region represents a volume which is enclosed by one or more surfaces. All right, so this would be if we're invoking divergence theorem. All right, so up here, for instance, you could say that the curves shown above become closed surfaces. So if I were, for instance, to take a trace of a 3D object, then what would I be seeing? I'd be just seeing a contour, but that contour actually lies on the surface. So it's a simple way of visualizing things. And so let's look down here. We have an example of a trace of some domain. And let's say I had problematic points right within the domain, and there and there. So we mentioned from the 2D case that we have to basically remove these points. So the simplest thing is to draw a contour around this point and a contour around this point. But this is a trace. So a contour in a trace format would represent basically a hollowed out sphere or closed object with a closed surface, which excludes the point that's problematic. So if we had two problematic points, you'd have these two hollow spheres embedded within the object, and then you have the external sphere. So everything that's shaded here in the sort of a yellowish color is considered to be the region. Right, so just a summary then, problematic points, black and red to your right, lie in the domain or volume bounded by the three surfaces. The orientation of the bounding surfaces is shown outwards from each surface boundary in this picture. And if you want to look at this in more detail, you can look at this here, this URL. So more or less, this is sort of the picture we're looking at when we extend things to 3D. All right, so let's look at not simply enclosed 3D region. And so this is a trace. So if this is a simple sphere and hollowed out sphere, then there would be the inner surface of this hollowed out sphere. And let's take that to be direction S2. That's the differential surface area vector. And this is the differential surface area on the outside. So how do we deal with this type of problem when it's not simply enclosed? Well, the simplest thing to do is to introduce a cut. Just cut through it. It's almost like taking a peach and opening it out. And so this is the picture you would see. This is actually a perspective diagram, and this is to be a trace of the same region. And so we create two separate halves. And of course, we put them back together again, but this is simply to visualize things. So now that we've cut them in half, then we have this region for part B, which is closed, basically enclosed by surface. How many surfaces? Where there's this hemispherical surface, there's this flat planar surface, and this inside hemispherical surface. Similarly for the top half, we have this bottom planar surface, we have this interior surface, and this exterior surface. And the arrow vectors already have been indicated here in terms of direction. So if this is taken to be outwards, then minus S2A is referring to being inwards. And here basically this one's pointing in this direction, which is by convention correct, and this is pointing in this direction, which by convention is correct. So as far as convention is concerned, the arrows I've shown here are correct for applying the divergence theorem for the upper hemisphere, hollowed out, and also for the hollowed out lower hemisphere. All right, so what we do is we apply the divergence theorem, therefore, to each sub-region after introducing the cut. And so for the top, this is the divergence theorem for the top part, and this is the divergence theorem for the bottom part. Now we add these two equations together, and you realize that D3A is equal to minus D3B. So when you add the two together, this surface and this surface, when added, basically, the flux contribution cancels. And so finally we're left with the expression shown here, that the closed surface integral, which is when you join the two together, is just going to be a contribution from S1, which is the exterior surface, contribution to the interior surface, but here at minus S2, which is pointing inwards, not outwards. Or alternatively, you want to reverse the direction so that it's pointing in the opposite direction. You can make this S2, but in that case, a minus sign goes here. When you glue these two volumes together, this is the total volume of interest, which is enclosed. So this is how you would apply the divergence theorem if you have basically a hollowed out region. And lastly, what about problematic points in a 3D region? Here I've shown just traces. And so for instance, you have a point here, which you basically want to avoid, and a point here, which you want to avoid. And so we basically have drawn circles around them. So in actual reality, in a 3D diagram, this would be basically a hollowed out sphere and a hollowed out sphere, which encircles these points. And so in this case, if you want to apply the divergence theorem, the simplest thing is to introduce a cut like we did before. And so now you have the region above and the region below. And you can apply the divergence theorem to this problem and the divergence theorem to this problem. Then add the two results together, and you end up basically with the expression that's shown here, which is exactly the same as what we did on the previous slide. So there are ways of dealing with problems, if you need to apply the divergence theorem. And so the notion of introducing cuts is a very simple technique which is used frequently. Anyway, so that more or less summarizes Lecture 31B. Thank you for listening.